In this lab, we're going to take a look at gradient descent and automatic differentiation as it is implemented in PyTorch. So without any further ado, let's dive in. We start by looking at how PyTorch uses a library called Autograd for automatic differentiation. I have run the first cell here, which installs all of the dependencies that we're going to use for this particular notebook. You will see that I've got here torchviz and torchview, which are useful libraries that are going to allow us to visualize what's happening whenever Autograd does a differentiation. So I'm going to start by instantiating a tensor, which I am going to call x1, and I'm giving it a value of 1.2. And now we're going to take a look at this particular property of a tensor called requires grad. This is what PyTorch uses to tell the automatic differentiation framework whether or not we want to calculate a derivative for that particular parameter during backpropagation. We'll see this in practice in a second. But as you can see, by default, this is set to false. Now, I am also going to instantiate another tensor that I'm going to call W1. You can imagine that X is the input and W1 is a weight. Of course, this is quite simple because I only have one input and one weight. But this weight, being a parameter as we saw, is going to have a gradient. So we've got require gradient equals true, and you can see that this is effectively reflected here. Now, if we perform an operation x1 times w1, and we store that operation in the output variable, obviously the output is 3.6, we can take a look at the grad property of both x1 and w1. These are set to none because obviously we haven't done the derivatives and we haven't calculated the gradients yet. This is what PyTorch helps us do via Autograd when we call the backward function. So the O variable, remember, is the outcome of this operation, and I can call backward. Here I am passing retain graph because I want to make sure that it doesn't delete the graph. I want to show that to you in a second. But anyway, if we take a look now at the gradients, x1 doesn't have a gradient because remember it had require grad set to false, but w1 had a gradient. So now the derivative has been calculated for it, and you can see that the derivative is 1.2. Now, as I said, in this training, in this course, we don't really go into the details of mathematics and how derivatives are computed. But if you want to take a quick look at this, essentially Autograd is implementing differentiation rules, and the Wikipedia page is quite informative about this. There are some elementary rules to calculate derivatives, and this is essentially this 1.2 essentially comes from applying some of these rules. So our O is essentially a function of the weight W1, and we've got x1 times W1. That's exactly what we calculated here. Now we can use the product rule because this is essentially a product of two functions. Now the first function is the weight and the second function is x1. And for all intents and purposes, what we want to understand here is that when we look at this, x1, which is the input, it could be the value of a pixel in an image, for this particular iteration is a constant. And the derivative of a constant is essentially 0. Whereas the derivative of the weight with respect to itself is 1. Now this is quite important because we can then apply the product rule that again you are going to find here if you want to take a better look at it. And essentially this means that we are doing the sum of the value of the first term of the product multiplied by the derivative of the second term and so on, and the value of the second term with the derivative of the first term. So if we take a look at this very quickly, you can see that the derivative of the output with respect to the weight is essentially u, which is w1, so the value of the weight multiplied by the derivative of x, and the derivative of x, because x is a constant, and we have a rule to derive the constant term, which essentially says that the derivative of a constant is always 0. So this term here, this first term, cancels out. And then the second term is the value of x1. This is this v here, the value of x1, and then the derivative of the weight with respect to itself, which essentially is 1, and this ends up giving us x1. Computing the derivatives of simple functions can be done by hand, as we've seen, but if we have a very complex function, it is really hard to do, and we have to essentially keep track of everything that's happening, all of the single individual operations which are involved, and we saw that this can be done with the computation graph. Now, we can visualize the computation graph with this make dot function. So we pass O. You remember O is the result of our simple computation here. And when we run this, you will see the graph that PyTorch has created to keep track of these operations. It's a little bit difficult to read, but W1 is obviously the parameter which has been multiplied. So you can see here, this is the multiplication operation, and it's been multiplied with a value here, which we're not really tracking the name of, but that value would be, where is it? That value would be x1. And then the output is this one over here. Now, don't be confused by the values in parentheses here. This is just the size of the tensor, not the value itself. So obviously here we're working with one-dimensional tensors because it's a very simple example. Okay, so we're now ready to take a look at a more complex example. This is the simple perceptron that we had in our episode before. And as you can see, it's got x1 and x2, which are two inputs to the perceptron, and it's got w1 and w2, which are two weights. There is like the product and then the weighted sum, and we have the bias term, which gets added to the product. Then we have an activation function producing y at, which we can say is the prediction that our perceptron is making based on the two inputs. And then we've got y, which is what we are actually expecting the output to be. So the true value when x1 and x2 have got a certain value. So we do a simple loss function by calculating the difference between y at and y, and that gives us the loss. So let's implement this. We are instantiating all the variables and we're giving them some dummy values. You will notice that W1, W2, and the bias, these are the parameters of our network, and these are the variables that require a gradient. So we are essentially saying that we want PyTorch to calculate the gradients of the loss with respect to each individual parameter. The other difference that I have here, obviously I have the weighted sum. So this part here is up to this point. And then instead of tonnage, I am using ReLU. It is just easier for displaying a nicer output. And let's run this. And then we've got 2.66. This is the output of our network. Now let's create y, which we're going to instantiate to 0.5. So here what we are saying essentially is that when x1 is minus 1.1 and x2 is 2.4, we are actually expecting the true value to be 0.5. And then we are calculating the loss as that difference, and the loss is of course 2.16, as it is clear from this. Now we do the backward pass, and during the backward pass, what's going to happen is that using the differentiation rules, this is going to calculate the derivative of the loss with respect to each of these parameters. And specifically, we've looked at some of these rules, but the main rule that it's used here is the chain rule, because you basically have a perceptron is a function composed of other functions. So that's what this is using. And this ends up essentially multiplying partial derivatives by one another. It is important, you don't have to understand the detail, but it is important to understand that this chain rule essentially involves the multiplications of derivatives together. You can imagine that when you have a larger network and you have a very small derivative of something which is 0, and then you multiply that, you are gonna end up with some issues because numbers are gonna get very small or 0. Whereas if you have very large derivatives as well, you are going to have another problem, which we typically call exploding gradient. But don't worry about this now. We can come back to the backward pass that we've done. And now if we look at the gradient variable, you can see that indeed the gradient for each of these variables has been calculated. And we can also take a look at the computation graph. And so this is how PyTorch has accomplished this. This graph is exactly the same as this. It is just vertical, as you can see. So we've got weight 1, which was multiplied by x1, weight 2, which was multiplied by x2. These two values were added together. So basically this node here. And then we have got the bias, which was added to the output of this. And then we applied ReLU. And then we did a subtraction from the expected y value, and we got our result. So that's the computation graph. Now, just to remind you, why are we doing all of this? Essentially, these derivatives tell us the influence of each of the parameters on the loss. And if you remember, the problem of training a network can essentially be seen as the problem of minimizing the loss. So the derivative with respect to a weight tells us how much a little increment in that weight is going to affect the final loss. So we know how much we want to change or tweak that parameter to minimize the loss. Let's take a look at this. This is exactly the same expression that we have up here. So I'm just gonna run it. And as you can see, actually, let me add, where is it? Let me also add the calculation of the loss. There it is. So obviously the loss is exactly the same. Now, if you look at these derivatives, the bigger one is the one for weight 2, which means that a little increment in weight 2 is going to make the loss go up. Let's check this. So we've got weight 2, and I'm going to add 0.1. Oops, sorry. 0.1. Look at the loss. And indeed, the loss has gone up. And if I add a little bit more, that makes the loss go up a little bit more. Likewise, if we take a look at the derivative for W1, this is a negative derivative, which means that if we add a little value to W1, the loss is going to actually go down. Let's take a look at that in practice. So that's W1. I'm going to add a tiny value. So let me first run this, look at the loss, and now it's gone down, and it keeps going down. And this is essentially what we do in gradient descent. Obviously, we do the contrary of what I have just done. So what we want to do, for every parameter, we want to update that parameter in the opposite direction of the derivative. So in this case here, I want to subtract a small number from here because I want the loss to go down. In this case, I want to add a number because it's negative. And in this case here, for this tensor, I also want to remove a small value. And this should make the loss go down. And that's essentially gradient descent. Obviously, we repeat this many times until the loss becomes small. But we'll look at this specifically in the next episode. Okay, now let's see this in practice on the perceptron we built in the last lab. If you remember, this was a perceptron to recognize small handwritten digits, the MNIST dataset. I've got the perceptron here. It had a few layers, the input layer which takes the image, and then the output layer which gives us the 10 classes or the probability distribution for the 10 classes. I am going to make a random image. And if you remember, the image has got this size, and then I'm adding one dimension for the batch. And obviously this is a tensor which contains one element in the batch, and that's this fake image that we've created. I've instantiated the model, and now we pass the image through the model and we get the y-hat prediction. Okay, so that's the probability, not the probability distribution. These are the logits which we can turn into a probability distribution using a softmax activation. And now we calculate the loss. Obviously, the loss we had before was a simple subtraction, but here, as we said, we have a probability distribution across 10 classes. And what we want to do to compare that probability distribution with the true labels, we have the true labels which are hot encoded. So, for example, in this case, I have made a tensor, and hot encoding means that it's got 10 elements, one per class, but only one of these elements is set to 1. So in this fictitious scenario, we are basically saying that the image we have randomly generated should be a 2 because we have activated the 2. Or it depends. It could be a 1 if we start counting from 0. It depends where we put the 0 in this tensor. But now that we have y, we can use the cross-entropy loss to compare this probability distribution, so the logits that the network has produced with the true hot encoded labels. And I am actually going to do this, and this gives us the loss. As before, we can call backward, so it causes all of the derivatives to be computed. And we can see, if we look at each parameter of the network, for example, the bias tensor and so on, that these have got derivatives calculated. The grad parameter has been calculated for all the weights and all the biases in all the different layers of this network. So let's now take a look at the computation graph for this run of the perceptron. So this is, you will recognize a weight matrix for the first layer. You recognize the dimensions. This is the input dimension, and this is what the layer is gonna output. Just to show you what this is, that would be the matrix for this particular layer. And of course, all of these are matrix multiplications that are done with the input. So you can see here the matrix that we've got here. This is the input. So this is the fake image that we've created. And 1 is because obviously in our batch, we only have one image. If we added other images, this would be obviously larger. And these are, and there is a matrix multiplication that happens. And then you've got the ReLU there, and so on and so on. You can see this is the second layer of the network, so the second matrix, which again gets multiplied until we get to the final loss. I don't think it fits in here, but you can see how the derivatives are calculated. To finish this episode, I wanted to show you a little bonus thing that you can do with the torchview library. So we have our model that we have instantiated, And we can see not the computation graph, but the actual computations in the model. So for example, we're giving it a batch size and an input size, and this is going to come up with random input. So it's going to generate a random image or number of images, and then it's going to pass them through the model and we can visualize that. And that's a very, very nice way of visualizing. Let me see if I can make it bigger. It's a very, very nice way of visualizing this. You can see the input tensor. This is the size of the image, and this is the size of the batch. The first linear layer gets this as an input and outputs this. Then there is the ReLU layer, then the other linear layer, and so on until we've got the output tensor. So very, very nice way of visualizing all of this.